Okay, here we go. Let's go to the whiteboard. We have to, so what we learned last time was that we broadened our understanding on the man-made number system. We thought it was just the real line, but now we know that we have expanded it into a plane that we call as the complex plane. We had just real numbers on a line. Now we have what are called complex numbers. We called them complex numbers on a plane. Right, so we'll begin from there, and you have to learn a couple of terminology related to complex numbers, and we will write those down today. That's where we are going to start. So let's turn this around. That's my pen. So we will start with a subtopic, and I will set my subtopic is some terminology. This is some terms, mathematical terms that are related to complex numbers that you have to be familiar with in order to proceed forward. Okay, so you just learned what complex numbers are. So let's learn the terms related to them. So subtopic, some terminology. Okay, write with me. We now know that all numbers that exist, I'm using capital all and in red, all numbers that exist, exist on, I will remove this, exist on what we came to call, the, in red, capital C, complex plane. We now know that all numbers that exist on what we came to call the complex plane. This means I'm sorry, not this means. I'm sorry. Consider any complex number Z in red. You know that Z is the notation that we use to indicate a complex number, Z, okay? Consider any complex number Z anywhere on the complex plane. anywhere on the complex plane. Then let's draw a small complex plane. I will draw it here. Oh, I will use, remember we were using green for the real line. And blue for imaginary line. Right? So you, when you label in your when you draw your complex plane, you have to label the lines. And remember, the real line and the imaginary line can also be called axes. You can say real axis and imaginary axis, as if it is a coordinate plane, like as if, right? Because it looks like one. So sometimes people call the real axis and imaginary axis. I personally don't like that. It's the real line and the imaginary line, but it's okay. Right? So this is imaginary. Like you are labeling the X and the Y axis, you have to label. This is imaginary. I will just say imaginary. Okay. And then this is real. This is where your 0 is. Oops, I meant to draw in black. This is your 0. The number 0 is there. Now let's consider, like you can take a complex number anywhere you want. I'm just going to pick one right in the, like the first quadrant somewhere here. Number somewhere, say here, right here. This is my Z. Here's my Z. Okay. Then, so this Z could be anywhere on the plane. It could be on an axis. It could be on the real line. It could be on the imaginary line. It could be in between space. It doesn't matter. Wherever it is, everything that we are going to write now afterwards this is true for any complex number anywhere on this plane. You know that if a number is on the real line, it is purely real because it has no imaginary component. And if a number is on the imaginary line, it is pure imaginary, no real component. But in general, when you take a complex number on the complex plane, there is a way in which that we write the complex number in general, and it is true and correct for any point, any number, anywhere. Okay, so I have marked it here. So this will have some real component. We actually, so these are the words that we are going to learn. These are called parts. We say real part and imaginary part. It's going to have a real part and an imaginary part. And this would be something I, so this is B. And for I will use, what will I use for I? Shall I use red for I? This is BI. You know that on the imaginary line, you have 1I, 2I, 3I, 2.5I, something I. It's the imaginary line. It's the imaginary axis. Right? So mark those two. And then write any Z. Now we are considering this particular Z. Any such Z, any Z can be written in the following form. In the following form. What is the form? Z is equal to A plus BI. I'm just now you don't have to use this color coding that I'm using. You know that I like doing that. That's why I do it. If you have color pens, go ahead. But if you don't, it's fine. So A plus BI. Here A is whatever the component, whatever that number, depending on the position of your complex number Z, the real part that it has is A. It can be 5, 10, 9. It's a number on the real line. You see it, right? It's on the real line. And BI is the imaginary, the number on the imaginary line. So this A and B, the two numbers, A and B, this is part of the terminology. They are called, this A is called the real part of your Z, and this B, without the I, just B is called the imaginary part of your Z. And A and B are, now listen very carefully, A and B are real numbers. A and B are real numbers. Do you understand that? A is a real number. This A here, it's always a real number. Some number, 10 or 5 or -3 or 5, 11 or 1004 or whatever, half, whatever. It's a real number. This B over here is also some real number, right? Because I we have separated out. So this I is what makes that term imaginary, but the coefficient B is a real number. So for example, think of some possible Z's on this plane: 2 plus 3i, minus 4 plus 7i, half minus 10i, right? Do you see that the A and the B, when I say, they are real numbers? They are both real numbers, but A is the real part, B is the imaginary part. How much of I have in this Z? BI. It's like if you said 2I, I have 2 of imaginary, the imaginary part is 2. Okay, so I hope this is clear. And the other thing is just whole A plus BI. I talked about this last time too. A plus BI is one number. That also might be a little cognitively, it might be a little difficult to take in at once, that it is one number. When you say 2, for example, I don't write this. If I write 2 plus 3i, if I write 2 plus 3i, it's one number, right? This corresponds to a single point on this plane. 2 plus 3i is somewhere on this plane. It's a point. So it's one number. It has a real part 2. It has an imaginary part 3. Part vanilla, part chocolate. Okay, so hope that is clear. Right, so I will label this here itself, but I'm going to give you in point form this terminology. But in this where you have written this, I will just point to this A and B, and I will write this A is called real part, It's the real part of the imaginary number, and this is the imaginary part of the real number. Okay, and I will say in brackets here, both A and B, they belong to real. They are numbers from the real numbers. They are two numbers from the real numbers. Yes, Malit, I thought as much when you were not in the participant list. I knew you must be still sleeping, snoring and sleeping. Okay, so this we were writing this, Malit, just okay. So we'll begin the so I'm giving you in bullet points. First bullet point. We'll put the bullet points in this color. Here's the first bullet point. The first terminology is what we call, I already labeled it here, the real part and the imaginary part. Okay, but I will write it now. Real part of Z. First one is real part. We call it, so like you can say component, but the term is part. Real part, imaginary part. That's how you say it. Okay? Real part. Real part of Z. The notation for this is RE in brackets Z. How do you read this? Real part of Z. Real part of Z. Of Z. Real part of Z. Shortened notation. So it's a term. It's part of the terminology related to complex numbers. Real part. It's a thing, okay? Real part. Under that, right? That number A, your number A, I will use my colors. A is called the real part of Z. And then similarly, second bullet point, imaginary part of Z. The notation is im of Z. Im bracket Z. How do you read it? Imaginary part of Z. The shortened notation is im bracket Z. Imaginary part of Z. What is it? It's the coefficient of the I term. It's how much of I, how much of imaginary flavor you have in this number, the amount of chocolate. Okay, it's the number B. So B, the number B is called the imaginary part of Z. It's called the imaginary part of Z. Just the B. You don't give it the I. If I ask you what's the, like if you have a number 2 plus 3i, what is the imaginary part of this number? 3. Just 3. Not 3i. I'm already asking what is the imaginary part? 3 is the imaginary part. 2 of real part, 3 of imaginary part. Okay, it's like the rate, it's like the, you know, how much of this and how much of that. 2 units of real, 3 units of imaginary. Units, we will say like that. That's more clear, I think. So this number is comprised of 2 units of real, 3 units of imaginary. Okay. Next one. For the next one, I have to add something to this diagram. The next 2 terminology I'm going to give you. Oops. My screen went black. Did you see anything happening on your screen? Did I go blank? No. Did I hit something on the side? I wonder why that happened. It went just completely black and then okay. Right. So I'm going to add to the same diagram. Okay, what I was saying was the next 2 terms are going to describe the next term is going to describe the size of Z. Now you have to think about this. Okay. Now when you just had real numbers, when I just say a real number, you have a sense of how big that number is, how big the size of that number, what we call the magnitude. Remember, the modulus is the size of a number. Like when I say the number, you know how big it is. Like when I say 10, I mean, it's 10. It's 10 units large. If I say minus 10, that also is 10 units large. You have a sense of where it is on the number line and also how big it is. If I tell you 2 numbers, you can immediately tell me which number is bigger, isn't it? Like, for example, bigger in the sense, which number has the bigger magnitude, not bigger magnitude, the size, the length. This is why it's useful to think of numbers as an arrow. The length of the arrow is the size of the number, right? You know that 3 is larger than minus 10. 3 is positive 3 is larger than minus 10. But in magnitude, modulus, minus 10 is larger. You know, it's far further away from 0 than 3. So the magnitude wise, the size, the length, minus 10 is longer or larger, right? Like, so if I say any 2 numbers to you on the real line, you immediately know that you immediately have a sense of its size. But now when we talk about complex numbers on the complex plane, when I say 2 plus 3i, how big is that? Like, what's the size of that? A number should have a size, a number should have a magnitude. 2 plus 3i, is it bigger than 1? Like, what's the size of it? You know that size of a number is defined as, and it makes sense to us why it is defined that way. It's how far that number is from 0. That's the size, right? Do you understand? Let me go to a new page. We are continuing the same note. I'm sorry that I can't use the, what do you call it? This Microsoft whiteboard. I could have just gone here and there on the same screen in that. Right. Anyway, so what I'm saying is this. What is going on? Who's putting ticks? Am I putting ticks? Yes, I'm doing that. My mistake. Okay. Like when we just have the real number line, I forgot what I wanted to say actually. So if a number is here, this is the magnitude. If a number is here, this is the magnitude. How far that number is from 0. But if I say 2 plus 3i now with the imaginary axis and the complex plane, if I say 2 plus 3i, immediately you would know in which quadrant it is, where it is on the plane. 2 plus 3i means 2 and 3 both are positive. So somewhere in here. But how big is it? So that how big means Just like we think of when you have a number here, it's this distance. The distance from 0 is the size. And if you have a number here, it's this distance from 0. Just like that now. If you have a number here, the size means how far it is from 0, the distance from 0. It's called modulus. Modulus, same idea. It's not a new concept. You have this concept already, modulus. You just have to extend that into complex plane now. So if I want to know what's the size of, or what's the modulus of 2 plus 3i, what that means is how far from 0 is this point on the complex plane. That length is what its modulus is, right? And it is not immediately, we don't immediately see it. You have to calculate it. Like a position vector, like you can think of any number as a vector from 0, like a position vector pointing to its position from 0. Then the length of that arrow is the modulus. Okay, size of a number is how far that number is from 0. This is the definition of modulus. So if I say modulus, modulus sign of 2 plus 3i, we can calculate it. Modulus of 10 is 10. Modulus of minus 3 is 3. I mean, for a real number, modulus of minus 2.9 is 2.9. Very, there's nothing to do, you know it immediately. But modulus of 2 plus 3i, wait a moment, let me calculate it. You need to calculate it. And the calculation is very easy. You can use your, if your number is here, how can you calculate this distance? This is 2. This is 2, this is 3, isn't it? 2 plus 3i means this length is 2, this length is 3. A simple Pythagorean Pythagoras theorem you can apply to calculate that r. So this is the whole story. So I have to just go back to this diagram and add. So what colors do I have left now? Color. Okay, so I wanted to add to your diagram. Even in red, I wouldn't mind. I think red would be better. Yes, Hatri. I don't know, Nathan, what you missed. I don't know. Oh, accidentally you raised your hand. Can you add this? Oops. Let me actually take this out. Okay. Connect 0 and your complex number z. And that length of that line, mark it as r. Like radius. Okay. Nathan, don't be sad. Now I know that when you get disconnected, you come back and say, I got disconnected. What did I miss? I don't know what you missed. I don't know when you got disconnected. Just stay on, ask for the recording, or if you have missed to write anything, you can let me know that, Miss, I didn't see that part. Can I write it? But I wouldn't know what you missed. How do I know what you missed? If you just keep listening, you will realize, I have missed from you. You only know at which point you got disconnected. So you only can figure out how much you missed, and I will send you the recording. I don't know, is it 1 minute or like 5 minutes you missed? I don't know. So I don't know which part of this you missed. Okay, right. So this length you mark on your diagram by connecting the 0. Let me. It's always a good habit to show 0. So connect the 0 point. 0 is another complex number. Any number on this plane is a complex number. 0 and z. Connect 0 and z. That length is r. And this angle, can you mark that also in your, oops, I want it to be in the same color. This angle, theta. Okay. So your next term, I'm going to the next page. Okay, I'm going to the next page. Your next third bullet point. modulus of Z, And for this, we have a couple of different notations. Modulus of Z, you already know the word modulus. When it comes to the modulus of a complex number, here are your notations. You can say your normal notation with the two lines like that. Modulus of Z. How do you read this notation? Modulus of Z. That's one way of writing it. Or this R that I indicated on the diagram is a symbol, is a standard notation for modulus. R. You can just say R, or you can read this R as modulus of Z. Or sometimes we also use this. We say mod of Z. All these mean the same thing. Three different notations for the same idea. Modulus of Z. Okay. And what is it? What is it? Let me go back to this just to see how I wrote this. Okay. Oops. Oh, yeah. What happened? Oh, I have skipped this page. It's fine. Okay, then right under that, mod. I will use that last symbol. Is modulus of Z is, sorry, wait. Let me write in words. It's modulus of a complex number, write with me, number is, what do you mean by modulus? Is its magnitude or size, is its magnitude slash size. Or if I elaborate it more, it means its distance from zero. Its distance from zero. How far is that number from zero? Its distance from zero. You can like underline it. Distance from zero. So if that's what modulus means, when you have your a plus bi complex number, in terms of using the, like now your complex number is what? It's a plus bi. A plus bi, no, your Z is a plus bi. Don't write that. How can you find the modulus of Z? How can you find it? Therefore, mod of Z, let's go back to this diagram, and can you think? This R, if this Z is, let me write what this Z is. What is this Z? It's a plus bi, a plus bi. Shall we add that to our diagram? This Z is a plus bi. Okay, so you can see a right angle triangle here. That's correct, Hathi, very good. It's, you have a small right angle triangle. You can apply Pythagoras theorem. So actually, I think I will just quickly show you here. You have something like this, wherever your this is your zero, this is where your Z is. This length is A, this length is, this is a right angle triangle. This length is B. So this is what your modulus is. This, the length of this line, this line, and this is R. So R is equal to square root of a squared plus b squared. Very simple. So you have to do that little calculation. That's the modulus of a complex number, a squared plus b squared. Even if your number is on the real line, this definition applies, is valid. Even if your number is on the imaginary line, it applies. What's the modulus of 3i? That's very easy. Modulus of 3i is 3. It's 3 units away from the 0. And it's on the vertical axis. Do you see that? What's the modulus of minus 7i? What's the modulus of
7.
minus 7i? 7. Very good, yeah. It's 7 units down here from 0. So that length is 7. Because a, for this number, a is 0, b is minus 7. So even if you apply this formula, a squared plus b squared and square root, you still get 7. But that is, for that, it is very, it's visible. The size is visible. For any number on the real line or on the imaginary line, the size or the magnitude is just visible. There's nothing for you to calculate there. But if I give you like 9 plus 7i, then you have to do this, right? Okay. So I hope that is clear. Next is argument. Now, don't ask me who came up with that word, argument. Argument of Z. Now, all these are attributes of your complex number. We can talk about the real part of your complex number. We can talk about the imaginary part of your complex number. You can talk about the modulus of your complex number. You can talk about something called the argument of your complex number. And what is that? Argument of Z. It's just that angle that I marked, theta. It's called argument. I actually don't know the history of that term. Who came up with the word argument? Why is it argument? I don't know. In Sinhala, is Tarindu here? I don't remember what we call it in Sinhala. What? I can't hear.
No, it's Mihil.
Mihil?
Yeah.
Mihil, මොකද්ද Mihil සිංහලෙන්?
තර්ක කරනවා කියලානේ කියන්නේ.
මක්කනවා?
තර්ක කියන්නේ අර argument කියන එක.
තර්ක කරනවා. ඒක තමයි no. I mean in normal language, like you argue means that you know තර්ක කරනවා. Yeah. That's not the meaning. That's why I'm saying, who came up with this? Why do we call this argument? That's not the meaning we have here. So it has a different meaning, and in Sinhala we have a different word for it. But you're right. It's like the direct translation of argument is tarka karana. Malit say, maybe yeah. Malit has a possible explanation as to why it is called argument, because maybe people for a long time people argued what word we should come up with this, and finally they said, okay, let's call it argument. Anyway, so it's the angle. Argument is no relation, right? It's the angle. It's the angle that the line connecting 0 and the number makes with the positive real axis, that angle. Okay, what I marked in the diagram. This angle theta, that your complex number, the line that is connecting your complex number and 0, that line makes with the positive real axis or line is what the argument is. Argument is the angle. So when you know the argument of a complex number, you know where it is, like where it is, which quadrant it is. So if the argument is an acute angle, you know you're on the first quadrant. If it's an obtuse angle, you know you're in the second quadrant, and so on. Like the angle the argument tells you kind of where it is, like the quadrant it is, right? So it's useful, it's something useful. And it is used for other things as well later. So you will see what all that is. So argument of Z has two notations. Which color we write notations? This. One is just simply theta, as I have marked in the diagram, or we say arg of Z, arg of Z, arg of Z. You read it as argument of Z, argument of Z. Capital A or simple, doesn't matter. Like I will put simple, arg of Z, because for mod I wrote simple M. Doesn't matter, mod of Z or arg of Z. Okay, so what is it? Let's write that. Argument of Z, right under this. Argument of Z is the angle, theta between the positive real, you can say real line or real axis. Let me use the word axis here, just so that you know both. Real axis, between the real axis and the line joining Z and 0, Z and 0. That line I have drawn, it's the angle between the positive real line and that line. So you can say Z and even you can say origin, but that's 0 actually. So this angle theta is measured in two ways, just like in trigonometry. Like we have made standards here, right? We have like conventions. We have agreed on certain ways of measuring it. So there are two ways in which you can measure that angle. One way, so I will try to fit that part in here. I have only little space. You write, it can be measured. It can be measured or it can be like expressed in two ways. It's measured or expressed. In two ways. You can give it as an angle from, so you can give theta. Let me first write it and then I will explain. As an angle from minus pi to plus pi. That means, like if I give a small diagram, that means if you have your line like that and if you the two lines like that, you measure it this way up to here or you go other direction. So you're anyway you're covering the whole circle, 360. You give it as a positive angle going this way, or you give it as a negative angle going that way. You start measuring from the positive real axis. Your start is here. From there you measure, okay? So that's one way, is giving it in this range. You go positive up to 180 and negative up to negative 180. Or, let me put a big or here, or the other way is, you can give your angle to be like the normal way, from 0 to from 0 to 2 pi. Like you go in one direction, this way and cover the whole circle. Is that clear? So wherever your complex number is on the complex plane, when you want to give the argument of that complex number, that angle can be expressed using this way. So you always you start with, there's no doubt about that. No, it's in the definition. It's the angle between the positive real axis and the line. And when you measure that, there are two ways you can do it. You can just always keep going anti-clockwise like this, wherever it is, or like if it is down here, instead of coming clockwise, you can go anti-clockwise. I'm sorry, I think I'm mixing up clockwise and anti-clockwise. I mean, you can go the other way and which has a negative angle. Is that clear? And then can we find the angle using, now when I give you the complex number is a plus bi, can I find that angle using my information in a plus bi? Yes, tan inverse, very good. This is all related. This is like coordinate geometry because it's like geometry now. This is we are working with a visual, and this visual is very familiar to us. It looks like the XY coordinate plane. Everything that you did there in a coordinate system applies to this. So I don't have space, but you write it nicely underneath this. I will squeeze this in here in this little space. You write so argument of Z. Oops. So you just write underneath here. I will write in the middle because I don't have space. Arg of Z, simple A or capital A, is what? It's tan, wherever your number is, it's tan inverse of B over A. Because A is like an X coordinate, B is like the Y coordinate. It is like the X and Y coordinates on a Cartesian coordinate system. So it's tan inverse B over A. Y over X, remember tan inverse Y over X in coordinate geometry for the theta, same thing. And actually, I wouldn't mind if you want to put like boxes around this. I don't mind, like they are important. Okay. The last terminology, now we did 4. Real part of Z, imaginary part of Z, modulus of Z, argument of Z. And the last one is, can I change the screen? Can I go to a new page? This says yes, if one more person can say. Yeah, okay. Last bullet point. This is called conjugate of Z, conjugate of Z. And the notation is Z star, a star like here on top, huh? Z star. It sounds like Z star. Z star. What is this? This is nice. Okay, this is something really nice. I like conjugate idea. Now, when you were just on the real number, and don't draw this, when you were just on the real number line, when we only knew the real number line, there was some kind of a symmetry here, symmetry around 0, right? There is no midpoint for the real number line, because it's an infinitely long line. You can't talk about a middle point. But 0 is like a middle point. Everything on this side of the line is kind of has a symmetry with everything on the other side. It's like it's only positive negative difference. But like 1, 2, they go like that now. 1 and minus 1, 2 and minus 2. There is a symmetry. And so for any number on this side, there was a counterpart. There was a corresponding number on the other side of it, -2. For 2, you have -2. For 10, you have on the same spot on the other side, -10. It's like a mirror. This is like the mirror. On 0, if you have a mirror, if this is your image, if this is your object, this is your image. This is positive, this is negative. And when you add them, you come to 0, isn't it? 2 minus 2 together, 0. When you add them, you get to 0, right? Any number here, add to the corresponding number on the other side, you come to 0, equal to 0. So there is, I hope you can see some like a symmetry thing, right? Now, similarly, when you are now in the complex plane, there is a similar thing going on. Now, when you had the line, the middle was the 0. Here, you think of the real line like a mirror. Now, if you do physics, you know this is how you mark a mirror. If you think of it as a mirror or the surface of water, it's like above water and below water. Like, can you split your complex plane into 2, the top and bottom? This is the boundary. Okay. Then, for any complex number on top, there is a similar complex number right below. It's like its image down here. For any complex number on top, you have a corresponding complex number below the surface, same distance away. If this is A plus BI, what would this be? Like it's a pair. What would the other one on the other side be? It's the one on the other side of the real. Now we make the distinction or the separation. The separation is the real line. We're talking about all the numbers above and all the numbers below. For any number above, there is a corresponding number right below it. If this is like, okay, let me actually put not A plus BI. Let me give a, let's say this is 5 plus 12i. Then what would this be? The one right? It's like the mirror image. What would be the mirror image number of that? If the real axis was a mirror, 5 minus 12i, very good. It would be 5 minus 12i. Do you all see that? Because the 5 didn't change, you're still there. 12i top minus 12i bottom. If this was minus 3 plus 2i, what would this be? What would be the corresponding number or the mirror image of, I will use the word mirror image, minus 3, very good Hatfi, minus 3, minus 2i. Do you all see that? This is a very simple thing I'm showing. For any number above the real axis, there is a corresponding number below it, the same distance away from the real axis, the right below it, vertically down to it. These pairs are called conjugate pairs. We say that this is the conjugate of this, or this is the conjugate of that. They are conjugates of each other. Okay. So
Okay.
these two are conjugates of each other. So in general, if you have a complex number a plus bi, the conjugate of that is a minus bi. The sign of the imaginary part changes because you're going down or you're going up. The change happens this way, right? You're not going anywhere this way. Real part stays the same. It's either the one above the water surface or below in the water. It's like if you think of this like a pond, right? And now why have we given this a special name, conjugate? Why? Because there is something nice happening. If you add a conjugate pair, now we still didn't talk about how to do operations with complex numbers. We still haven't talked about how to add complex numbers, how to subtract, how to multiply, how to divide. Can we do all these operations with these complex numbers too? We still didn't talk about it, but I will just tell you now, the special thing about conjugate pairs is that if you add a conjugate pair, you get a pure real number because the imaginary part cancels off. Same thing happens if you multiply a conjugate pair. If you multiply a conjugate pair, you end up with the pure real number, always. So that's some specialty, right? That is something special about these pairs. That's why we have given a special name for them. Conjugate. For any complex number z, you can talk about its conjugate. It's like its partner. Let's think about it as the partner. And if you multiply them or if you add them, you get a pure real number. Okay. Do you want to like sketch this diagram if it is helpful? In my note, I have not given any diagram, but I always...
I'm sketching it, miss.
Huh?
I'm sketching this. This is helpful.
Okay. So whoever who feels like this sketch would be helpful, this is, you can just have a sketch of this. This is imaginary, this is real. And just mark any point above the real line and the corresponding number below. That's the visual idea of conjugates. A lot of the times it is just, people just define if you have a plus bi, then a minus bi is a conjugate. That's all they say. But it has this nice visual relationship. It's like a point above. It's like when you think of R as a surface separating two medium, like in physics, like on top you have air and bottom you have like, not air, like it's like if it's a mirror, it's like the object and image. Okay, so if you need, you can sketch this and then you write. So I will erase all this because I need space to write. So I hope whoever who want this, you copied it. Then let's write conjugate of Z is the mirror image point of Z. Or let me just say mirror image of Z. Wait. Let's not bring in the word point. I mean, any number is a point on the plane, but let's just say is a mirror image of Z on the real line. Who's acting as the mirror here? The real line. On the real line. That is, if Z is equal to A plus BI, then Z star is A minus BI. Okay, so let's write that in red. if you have Z equal to A plus BI, Z star is A minus BI. These are conjugate pairs. Conjugate pairs. What's nice about these pairs is that I will put a little tick. It's another bullet point. The sum of any complex conjugate pair, the sum of any complex conjugate pair is always a pure real number, a pure real number. Also, the product of any complex conjugate pair or just conjugate pair, I'm just adding the word complex. Now, I'm saying this again, we still have not discussed how to add or how to multiply. I'm just telling you that here, you will see this in the next topic when we talk about operations. Complex conjugate pair is always a pure real number. Okay. Clear? Let's do a small exercise just to familiarize ourselves with these 5 terminology that we just learned. Real, imaginary, modulus, argument, conjugate of a complex number. All these are about a complex number. So if I give you a complex number, you have to be able to find or tell me what its real part is, what its imaginary part is, what its modulus is, what its argument is, and what's its conjugate is. Okay, so a quick little exercise. Can I change the screen? Yes.
Okay.
Thank you, Netni, for quickly responding. Little exercise. No, okay, it's okay.
Miss, can you show the previous slide for a second?
Find E of Z, Im of Z, mod of Z,
Excuse me, miss.
arg of Z,
Excuse me, miss.
and Z star for the following complex numbers. For the following complex. I can't hear you, Malik. No, I can't hear you. Are you telling me anything? You talked twice? No, I did not hear you. Did others hear Malik?
Slightly.
What?
I heard him said he was calling Miss.
Why am I not hearing you really well? Let me increase the volume. Is this the, okay. Say that again. Oh, can you put the previous slide for a second? Here we go. Okay. So find real imaginary mod argans and star for the following complex numbers. So you quickly do this is just to see whether you understood everything what we just did now. First one is 3 plus 4i. Second one is 5. Third one is 6i. Fourth one is minus 2 plus 3i. Fifth one is minus 4 minus 2i. The last one is 5 minus I. So I've given you complex numbers everywhere on the complex plane. Some are on the axis, some are just lying in some quadrants. For each of these, so take this as your Z. If this is your Z, what is each of these? Okay, I'll give you some time. And I think I can have a small break. I've been talking throughout. I hope it's okay if I take a small break until you work on this. So let me just switch off the. I'll give you 5 minutes, maybe. Would that be enough? I think 5 minutes should be enough. It's not the break. I'm taking a break. Okay, so work on this. Are you all done? I'm going to just Hatvi says Hatvi is done.
Not yet, miss.
Okay, okay. Would anyone like to fill the real column, the real part of each of these numbers? I started the first. I'm going to continue filling this table. What's the real part of the third number?
That one 0.
0, very good. Mod of Z is 5 here. Now, do you see something I want to point out here? Let me put the size of the first two numbers are the same. You know, the size of 5 is 5. And this number 3 plus 4i has the same size as number 5. That means both these numbers are the same distance away from 0. They are 5 units away from 0. Okay. Size of 6 is 6. Size of this 4. Root 13. Root 20. Root 26. Okay. Argument. You can give it as a positive or a negative angle, going this way up to 180 or going the other way up to minus 180, or you can give it as a positive number, positive angle. You need the calculator. Can somebody fill those in? I'm lazy to use the calculator. Did you give in degrees?
Yeah, miss. Give me a second, miss. I'm almost done.
Let's give it to the nearest whole number. Yeah. Correct. Yes. Oh, so you're giving us a negative. So I'll write both answers. Either you can say minus 56 degrees, or if you give it as an angle this way, like a positive angle, so it's in the 4th quadrant now. If anyone has that, please write it. I have kept a slash. So you're just giving a miss call. Did anyone write the angle to number 4 and 6 as a positive angle coming anti-clockwise all the way? What's the conjugate of 5? Five is on your mirror. Real line is the mirror now? No. Hatvi. Can someone else try? What's the conjugate of 5? For a point on the mirror, where's its image? No. Yes. Can someone else, now Hatvi gave, can someone else also tell me what's the conjugate of 5? Yes, Netni. 5 itself. You're on the mirror. So you're just there. Nothing will happen to you. If the object is on the mirror, the image will also be on the mirror on the same spot. Conjugate of 6i is minus 6i. This is minus 2 minus 3i. This is minus 4 plus 2i. 5 plus I. So can everyone check? Your answers, please, and let me know if there is any issue.
I'm back.
All good?